So in previous lecture, we reviewed the PyTorch, okay? So PyTorch, and also we also applied that into the object detection task, okay? And today we will gonna see how we can extend the deep learning architecture towards the segmentation task or the post-estimation task, okay? So as I explained before, this is the semantic segmentation task, which achieves the pixel-wise classification. So even though we detect the object with the bounding box representation, it has some pixels which is not belonging to the same class, okay? So this is the these are pixels which is belonging to the car pixels, but some of the pixels are not belonging to the same class. So this is problematic. So the computer vision researchers are proposing the semantic segmentation task, which detects the pixel-wise boundary, okay, for one class, okay. This is the semantic segmentation class task. And I mean, this is not trivial to achieve this semantic segmentation using the convolutional neural network. So the further research happened here, okay? And also we will see the post-estimation task, which is nowadays popular. So the post-estimation task, our aim is to estimate some landmarks of the hand or kind of the landmark of the human body, okay? So, I mean, here, given RGB image, our aim is to recognize their XYZ coordinate of the landmark point defined in the hand. So we normally define 4 key points for each finger and 1 key point for wrist. So there are, because we have 5 fingers, there are this number of key points for fingers and plus 1 for wrist. So there are 21 key points normally for the hand. And also similarly for the human body, we define around 20 landmarks upon the human bodies, like the torso, head, neck, and left arm, and so on. So for this kind of landmarks, we define around 20 key points. And our aim in this key point estimation task is to estimate their XYZ coordinate, okay? And nowadays, even we can extend this work to reconstruct this kind of full 3D meshes. This representation is called as mesh. And this was, as I mentioned, composed of 21 landmarks, but this mesh is a kind of dense representation. It is composed of around this number of vertices, okay? Compared to the 21 vertices, the landmark, this mesh is having more number of vertices, right? And also configuring 3 vertices, their faces are defined. So we call it as the triangular face. So we define the face composing the 3 vertices. So we call it as triangular face, okay? So this mesh is composed of both vertices and their faces, okay? So anyways, we can also achieve the reconstruction of this first 3D mesh using the deep learning nowadays, okay? And also for the human body, for the landmark, we define only 20 key points. But also here, we define around 6,000 vertices and over 50,000 face we define on the human body, and we reconstruct this kind of full 3D meshes of the human body, okay, using the deep learning. Anyways, this is the pose estimation task. Okay, we will briefly review the CNN architectures, which is used for achieving this pose estimation and also for achieving this semantic segmentation task. Okay. So as I explained already, this semantic segmentation task is achieving this kind of pixel-wise classification for given an image. Okay, so this is the input image, and this is the output of our semantic segmenter. Okay, so as you see, the color is encoding the different classes for the pixels. Okay, so for example, these pixels are representing the sky, and these pixels are representing the trees. Okay, and these pixels are representing the cat, right? So we want to make a neural network which can perform this kind of semantic segmentation. Okay, but the situation is similar to previous object detection task using the sliding window approach. Okay, I mean, if you naively apply this kind of CNN for the semantic segmentation task, the thing you can do is maybe extract some patches centering the target pixel, and you can move these patches around all images. And then for one patches, for each patch, you can maybe apply this kind of CNN architecture, which is trained on the ImageNet dataset, okay? And maybe you have to train another shallow layer to make it classify to some predefined segmentation class, okay? Maybe this is the thing you can trivially do using the CNN architecture. But this may take a lot of time because let's assume that this image, their width is this, and let's assume their height is this, okay? Then we have to apply this amount of CNN operations for obtaining the segmentation map for an image, okay? So this may take like few hours, right? This may take few hours to achieve the semantic segmentation for an image, okay? If it takes a few hours for obtaining the map for an image, maybe it is better to achieve the semantic segmentation by human hand, okay? So it means it is not efficient, okay? So the computer vision researchers have to consider another way to achieve this semantic segmentation using the deep learning, okay? They have to find more efficient way to achieve semantic segmentation using deep learning. And this is a solution they have considered, okay? So, I mean, this is the input, the RGB image, which has some arbitrary height and width. And this is our desired output for the semantic segmentation, okay? So in the semantic segmentation, we have to get some, discrete integer, which denote the class index, okay, for each pixel, right? And this color encoding is, denoting some different class index, okay? Anyway, we need this kind of one-dimensional the map which have just one channel and whose height and width is same as the input. Okay, we need this kind of output, and in the middle we can think of some differentiable architecture like this. So this might be the convolutional layer. Okay, samely as before, we used the convolutional layers at the earlier layers of the image classifier. Okay, so in the middle, we can obtain some feature vector. Okay, but we don't know which operation might be here. But if there is some operation that can expand, this is a kind of one-dimensional feature, right? So using the convolutional layer, we are tending to reduce the dimension of the 2D signals, right? And eventually we get some one-dimensional feature vector here, okay? And in the image classifier, we map it to some probabilistic vector, right? But here, our desired output is, again, 2D map, okay? This is the difference to the image classification, right? Are you guys following this? Okay. So we don't know yet which operation might be here, but we need some layers which can expand this one-dimensional feature vector again to this H by W dimensional 2D map. And at the same time, that layers have to be differentiable, okay? So if there is some layers like this, which have characteristics, having these characteristics, then that can be used here, right? And the solution is these layers, the transposed convolution operation could be used, okay? So this is the convolution operation you already learned. So this is the output map. Green is denoting the output map, and blue is denoting the input map, okay? And this gray things are denoting the filter corner, right? So if you apply filter corner like this, and applying the element-wise multiplication, and by adding them, you will get the 1 pixel output, okay? And then you will move the window, filter corner window by 1 pixel right, and do the same thing, and we'll get the next output, okay? And you will do this to get all the output, okay? By removing these windows, you can calculate the output map, okay? This was the convolution operation, right? But this convolution operation tend to reduce the dimension of input signal, okay? But we will use this transposed convolution operation to expand the dimension-reduced signal to more wider, to have more expanded dimension. So for example, this is the blue pixels are indicating the input image, and this green is indicating the output, okay? This is output, and this is input. And samely as before, we will use the 3x3 filter corner, okay? But, and also the operation itself is similar to convolution operation. So if you apply filter corner on this location, the thing you will do is multiplying the filter corner coefficients and also the input signal using the element-wise multiplication to get this 1 pixel output. So, and also you will shift the window, the filter corner window by 1 pixel, and we'll get the output here, okay? So these things are, the operation itself is similar to convolution operation, but in the transpose convolution operation, as you see here, if the input is 2 by 2, even though the input is 2 by 2, your output would be 4 by 4 signal, okay? So in the transpose convolution operation, the operation is tend to expand the input signal, okay? This is the difference between convolution operation and transpose convolution operation, but they are composed of addition and element-wise multiplication. Okay, so their final output is differentiable respect to their input and their parameters because they are composed of this kind of operation. Okay, so this kind of transpose convolution can be located in this part. Okay, because they are differentiable and they have the characteristics to expand the signals. Okay, and this is showing the more detailed operations of the transposed convolution. Okay, so this is some examples of this transposed convolution using 2 by 2 filter kernel and using stride 1 and using 0, 0 padding. Okay, and yeah, this is the 2 by 2 filter kernel. Okay, and this is the input map. Okay, and this is the output map. Okay, and by default, when you apply transpose convolution, we by default add the 1, 0 padding around the original input. Okay, so even though the original input was 5 by 5, because we by default apply 1, 0 padding, it becomes 7 by 7 intermediate map. And then we apply this 2 by 2 filter kernel with the stride 1 as the convolution operation. Okay, because we are by default add the 1, 0 padding around the image, the output size tend to be larger than the input image. Okay, this is the transposed convolution operation. And also, if you set stride as 2, previously here stride was 1. In convolution operations, stride was meaning how much we will shift this filter kernel. Okay, but in transposed convolution, this stride is meaning slightly different thing. So stride is meaning having some space between the input image. So the original input image looks like this, but if you use stride 2, then your image looks like this. So you had to rearrange the original signal to have some space like this. Okay, if you use stride 3, then this space might be 2, right, rather than 1. Okay, so this is the difference. The transpose convolution have the different meaning for the stride hyperparameter. So if you use stride 2, the output becomes even larger than the input image. So previously it was 5 by 5 image. So the output size slightly larger than the input signal, but here the output is actually doubled compared to the input image, okay? Because we have to rearrange the input signal having some space, okay? And then we apply 1-0 padding by default and apply the 2x2 filter kernel on it, okay? And this is another thing for having the 0 padding. So the definition of the 0 padding is also opposite to the convolution operation in transpose convolution. So these two are same as before, so we have to rearrange the input image like this, and by default, we have to apply the 1-0 padding. But because we set the 0 padding hyperparameter as 1, this happens. Actually, if you set padding larger than 0, it means actually removing the outer part, okay? Because you set padding as 1, we have to remove the outer 1 pixels, okay? So actually, this is opposite to the original convolution. In the convolution operation, if we set padding as 1, we will set the, actually we have to expand our input image by 1 pixels, right? And actually the input images are becoming larger, and then we set all the pixel values here as 1, as 0, right? But in the transpose convolution, if we set 0 padding as 1, it actually means deleting the outer 1 pixels, okay? So it becomes like this. And then we have to apply this filter kernel on this reduced image. So resulting in a smaller output, okay? So this is the transpose convolution, which have somehow different operation compared to the convolution operation. And actually this layer is also already defined in the PyTorch. So if you use this transpose 2D operation with the appropriate hyperparameters, then you can use this transpose convolution layer, okay? But maybe you are curious about why the name of this operation is called as transposed convolution, okay? So, I mean, this is the convolution operation again. So let's say this is the input image whose size is 4x4, and this is the filter kernel whose size is 3x3, right? And then this would be the output map. So if you apply this filter kernel on this, and applying the element-wise multiplication, and if you add all, then you will get this number. And if you shift it by 1 pixels right and do the same, then you can get this number. And also, if you do calculate the element-wise multiplication between the filter coefficients and the input values, and then add them to get this, right? And then applying this filter kernel on this location, and you will get the number here, right? This is the convolution operation. The same operation could be defined using the matrix multiplication, okay? So you can flatten the 4x4 input. This was the 4x4 input here, right? You can flatten it into the 16 by 1 dimensional vector. And also you can flatten this filter kernel to this kind of convolutional matrix, okay? in the middle, you have to add some zero, right? So there's some formula how to convert the filter kernel to this convolutional matrix. And then the thing you can do is multiplying this convolutional matrix with the flattened input signal, you can get this kind of output, okay? So this is multiplication, matrix multiplication, right? And then you will get 4x1 dimensional output, okay? And if you rearrange this to square signal, the 2x2 signal, then it would be same as the previous output, okay? So if you rearrange this output, you can get the same output signal here, okay? So I mean, here, what you have to see is the convolutional operation could be reformulated as the matrix multiplication. And actually in computer, this kind of matrix multiplication is easier to parallelize. So the implementation is mostly done in this way, okay? Anyway, you can think this convolution operation can be formulated as the matrix multiplication. And then if you apply the transpose operation, this transpose operation is meaning switching the column and row index, okay? So if you switch the column and row index for this convolutional matrix, then this type of matrix is obtained. So this is applying the transpose operation on the convolutional matrix, okay? And if you formulate, I mean, if you apply the multiplication for the input image, flattened input image with this transposed convolutional matrix, then your output tend to be larger than your input signal, okay? So here, what you will obtain is enlarged signal, okay, compared to the input signal, okay? So actually, what I explained here, this is the transpose convolution, right? This transpose convolution is having the characteristics like this because their convolutional matrix was transposed, okay? So, okay. So this, if your convolutional matrix looks like this, then it has characteristics like this. But if you apply the transpose on the convolutional matrix, it becomes the transposed convolution. Okay. Okay. So here, so I mean, even though the exact operations, they are similar to convolution operation. They are mostly composed of the element-wise multiplication and also the addition operation. Thanks to that, it is differentiable, but their characteristics are slightly becoming different to the convolutional operation, okay? So in here, the earlier part, it is composed of the convolutional layers, okay? And at the end, the later part, they are composed of the transpose convolutional layers, okay, to expand the reduced dimensional signal, okay. So somehow this is meaning to encode the whole images, okay, to encode their feature vector here, and somehow they model some, I mean, some interactions between pixels, right? Somehow the network have to understand the whole images, and that representation might be here. And we have to expand it again to some segmentation map like this, okay? So mostly they are called as encoder. The first part is called as encoder, and the later part are called as decoder. Okay. So this is the encoder-decoder architecture. Okay. So as you see, they are composed of the two modules. Firstly, they have encoder, and this is meaning stacking multiple layers, and they are stacking mostly the convolutional layer and also the pooling layers, also the nonlinear layers. And in the decoder, you can see they are composed of the transposed convolution operation to expand the dimension of the signals. Okay. And in the forward function, you can see the input are fed into the encoder and decoder in the sequential way. Okay. So this is the encoder-decoder definition. And by feeding the images into this encoder-decoder network and applying some softmax layer at the end and applying the cross-entropy laws, maybe you can train it for this semantic segmentation task. Okay. So, I mean, any differentiable layers could be trained using many X and Y input and output pairs. Okay. So if you apply the gradient descent, I mean, to make the output of these differentiable layers to be similar to your ground truth, then I mean, this network would be, after training, would be working towards that task, right? So this is the way to achieve it. Okay. So using this encoder-decoder, we no more requires this number of operations, we do not require this number of patch operations. Rather than that, we just input the original image once to obtain this type of, I mean, 2D formatted output. Okay. So are you guys following this? So easy, right? So if we constitute the differentiable layers using data, any kind of operations could be trained. Okay, that's the lesson. And another thing I want to share is this image generation task. So previously we saw this encoder-decoder architecture, right? This is the architecture that can achieve to output this kind of 2D formatted output. Okay. So people are becoming interested in generating the real images now, rather than this type of segmentation map. Okay. So in here, the map can have only discrete integer denoting the classes, right? If there are 20 classes, discrete integers would be ranged from 0 to 19. Okay. So this map was kind of defined like this, but here the images are composed of RGB 3 channels and may have dimensions like this. Okay, and also their pixel values are ranged from 0 to 255. Okay, this is the pixel values. Okay, so if we can achieve this, there is no reason to not achieving this kind of image generation task. Okay, so this was the paper that proposed this kind of thing. So what they did was they on purpose delete the center rectangles from the original image. And this is the human artist product. So to fill this blank, okay? This is not that realistic, right? So this is not that realistic, but this is the output from the encoder-decoder architecture, and also this is another output of the encoder-decoder architecture. So this is far better than the human artist product, okay? But this is bit blurred, and this is in high quality, okay? So this is the same encoder-decoder architecture, which is differentiable, right? And this is the input X, and this would be the output Y. So in this task, we don't have to even collect the labels. So previously in this image semantic segmentation task, we by our hand have to collect this type of label map, okay? So we have to collect this kind of segmentation map ground truth. But in this task, image generation task, we don't have to redraw even our ground truth image, because if you merge this was kind of original image, but we can delete this part and we can regard the original patch here as the ground truth, okay? So we don't have to collect even, we can anyway spend time for collecting the labels here, okay? And the naive thing we can do is training this encoder-decoder architecture using the same PyTorch code by applying this as input and this as the label information, okay? Okay, so are you guys following this? This is easy, right? We can train maybe encoder-decoder architecture using the data here, right? But the thing is, if you do that like that, using the L2 loss, so here the loss might be the mean square error loss, right? We can maybe use the loss function that can close our output Y similar to this ground truth patch, okay? But if you do this only, the output becoming like this. So it becomes somehow blurry, okay? So if you use only the L2 loss or the mean square error loss or MSE loss only, then the output would become blurry, okay? So here, what they do is they propose to use another loss, which is called as adversarial loss, okay? So I will briefly explain this adversarial loss, but if you are wanting to investigate this, then you have to maybe read this GAN generative adversarial network paper, okay? Maybe this is famous paper, but now this is kind of replacing with the diffusion model, right? But previously this was very popular, okay? So, but maybe it's worth to read. Anyways, the thing this paper is doing is they originally have two networks, which is the generator and which is the discriminator, okay? So this is hard to understand. So I mean, I explain it using this figure usually. So that generator is kind of the network which try to generate fake data. And discriminator, this is you can think this as the policeman. So the network that tries to figure out real and fake data. Okay, and these two networks are randomly initialized. Both are randomly initialized, but this generator is trained to try to generate some realistic data, fake data, but which looks realistic. Okay, but this discriminator, they are trained to discriminate the data which is generated by generator and the original real data. Okay, then it is somehow proven that this generator can generate the fake data which is quite similar to the real data. Okay, so anyway, I will first explain this loss function first. Okay, so this G is the random input, random vector sampled, and given Z, this is called as G, large G, and this will be denoted as large D. And the fake data, they will be denoted as G of Z, okay? Because we input the vector Z into the G, which is the generator, and then we will generate some fake data, okay? And real data would be called as X, okay? And the fake, it would be 0, the label would be 0, and real label would be 1, okay? And this loss is meaning that we will apply max, we will find the discriminator D first, which maximize this loss function. And then we will find the generator, which will minimize this loss function, okay? So first, we will find that maximize loss, this loss, okay? And okay. So given this log function, it looks like this, right? And this discriminator is actually the binary classifier, which will output the value between 0 and 1, okay? So if it is larger than 0.5, the class would be 1. And if the output would be less than 0.5, then the final class would be 0. So this is the binary classifier. So I mean, the both D of X and D of G, they are bounded to 0 and 1, okay? So D, their network's output is bounded to 0 and 1, okay? And this is the log function, right? And let's say the D of X is bounded to 0 and 1, okay? D of X is binary classifier, and their values are bounded to 0 and 1, okay? And this is the log D of X graph. And if you want to maximize this, when the d of x are bounded to 0 and 1, it means your d of x, this is the log d of x graph, right? And given when d of x is bounded to this range, the d of x becomes maximum when d of x goes to 1, okay? Are you guys understanding this? So by maximizing this, d of x will go to 1, okay? And also by maximizing this, if you draw the same graph, then you can find this need to go 1, and it means have to go 0, okay? So this is meaning that these two formula is meaning that if you apply the original real data x into your discriminator, your discriminator had to say it as real. And if you input the fake data g of z into the d, and it have to say it is the fake data, okay? So if you apply the first thing on the on finding to find the d, it means you have to find discriminator which can tell the real data as real and the fake data as fake, okay? This is the first part. And you also have to apply the second part. Have to find G, which minimize this V. And I will delete. Okay. And in terms of G, this part is constant. So now we can ignore this term and only can minimize this part, okay? And the graph would look like this. So this would be 1 minus dg of g. And the log function would be like this. And this log function would be actually representing this graph, okay? And your input would be bounded to 0 and 1, okay? And to minimize this function, this signal, this x-axis have to go to 0. And it means this have to go to 1, okay? So their conclusion is this. So by minimizing V, G have to train to make this as 1, okay? And it means in this case, D is fixed and only G is trained, okay? And for given D, given discriminator, given policeman, this G is trained to make the policeman to say is generated the fake data as real, okay? So this formula is kind of enforcing the generator, making the generator to generate quite a realistic fake data. So even this formula is saying that the policeman would be say yes, say real for the fake data, right? So even though the fake data is inputted the discriminator, the values are becoming toward the one, the real, right? So given policeman, the G is trained to fake the policeman, okay? To say it's generated data as real, okay? So this is the two signal. The policeman, the discriminator is trained to discriminate the real data, to say real data as real and the fake data as fake. But the generator is trained to deceive the policeman, okay? Deceive the discriminator, right? Anyways, this is the adversarial laws having another discriminator network, and the generator is trained to deceive this discriminator network, okay? So it becoming to generate, better quality images, okay? So if you apply, this is the same architecture, but using two loss functions. This is the mean square error loss, same as before. But if you add the discriminator network and apply another this loss function, this is the two loss function will be applied to this output of the encoder-decoder network. Then the output becomes better, okay? So here, if you apply both L2 and adversarial loss, the images generated is now in the high quality, right? Compared to this blood image, okay? So when you try to generate images rather than this kind of segmentation, rather than generating the segmentation map differently to the previous application, you have to use another loss function, okay? So you can see this is kind of similar to the realistic situation. So this is, so let's say this context, this encoder-decoder architecture as the student. So if we give X and Y, which is the question and answer, right? If we applying this L2 loss only is similar to giving some XY pairs, a lot of XY pairs to student, okay? Then the students are trying to mimic the previous XY pairs, but for some data, it is not generating high quality answers, okay? But if you have another discriminator network, and this discriminator network is trying to discriminate the student's answer is correct or not, right? And if this student is further trained to deceive this discriminator as if its answer is always the correct one, then the student will struggle, right? So its output, its answer becomes more realistic, right? So you can think this adversarial loss as that kind of context, okay? And also, if you apply only the adversarial loss, it will not work in this way. So because the student is not knowing the correct X and Y pairs, but if you apply only the adversarial loss, then student will generate only one realistic image, but it would not be coherent to the input image. So you will generate some random Z, which looks realistic, but it might not be consistent with the input X, okay? So here, input is this, but you will generate some random patch, which is not consistent with this surrounded pixels, but it looks realistic. So the student will generate that, okay? So that is also not something we are desiring, right? So we have to apply this too. So we have to let students know the the input and output pairs. And at the same time, we had to make the student struggle, right, to fight against this discriminator. Okay, then the output becomes more realistic. Okay. Okay, are you guys following this? So this is the image generation part, right? Maybe you can think that the image space that's kind of wider in space compared to the semantic segmentation output. So you can think we have to apply this kind of additional loss function, which to try it make in the high quality. Okay, and at maybe next class we will review. We will see how we can achieve this post-estimation task. Okay. Let's finish here and see you Wednesday. Okay. Thank you.